Alrighty, I think we'll kick things off and let people continue to log in as we go through introductions. First and foremost, hello everybody, and welcome to Strength and Flexibility: Finding the Right Motor Lead Cable for Your Application, a technical webinar with Champlain Cable and EIS. I am Lindsay Hartman, the Director of Marketing for EIS, and I am so excited to be joined by my dear friend Dave Dexter, Regional Manager at Champlain Cable. Dave will be leading us in our webinar today and reviewing manufacturing processes that provide improved flexibility and reliability above common XLPE cable products. So I'll be acting as our moderator today and monitoring our chat box. If you have any questions, need any clarification or additional information, please send us a message and we'll make sure that we cover it in our Q&A. Thank you so much to everybody for joining us today. And with that, I'm going to turn it over to Dave.
All right, everybody. Thank you, Lindsay. Thanks, everybody, for your time today. This runs, I don't know, roughly 30 minutes based on questions, and I think we have plenty of time for Q&A afterwards, so don't hesitate to ask questions. We're going to talk about motor lead wire today, some of the different products that are out in the market, and kind of compare those with the Champlain irradiated crosslink motor lead Exar product. We'll spend just a second on Champlain in general, if you're not familiar with us, just to give you a little familiarity. Then a broad overview of wire and cable and cross-linking as it relates to motor lead wire. Then the Exar products and comparisons between the common motor lead cables out there. And then some special considerations that you'd want to be aware of when selecting a motor lead product. From a Champlain Cable perspective, we're a fairly small company. We have 5 facilities, but we're not one of the multi-billion-dollar companies out there. We're very product focused, material focused, and high performance focused. Our headquarters is in Colchester, Vermont, and we have 2 facilities in El Paso, Texas, and 2 facilities in the Houston metropolitan area. As a timeline, we were founded in 1955 in Vermont to service mostly the aerospace and thin wall airframe wire. But in the early 70s, in 1972, we got into irradiation cross-linking and into the motor lead market space, originally with the old Reliance Electric. If you remember, that brand still exists, but the company Reliance Electric, 50 years ago, this is our 50th anniversary of the original Exar motor lead product. And we worked with them to provide a motor lead cable that was very tough, very oil resistant, flexible, and would be a cost-effective replacement against the next best at the time, which was FEP, which is very expensive and very stiff. And over the years, we've grown our capabilities, we've expanded our market presence, but the biggest thing, well, maybe not the biggest, but one of the biggest things that is we've grown from 3 irradiation cross-linking units to 8, and actually 9 coming on, 9 irradiation units, which is industry leading. Lots of capability there. So we speak of cross-linking. All right, so what is cross-linking? There are different methods of doing it based on, manufacturers, kind of what they focus on, how they want to get, the equipment they have to get that done, and the materials that are used. So cross-linking is the process of permanently linking the plastic molecules, the polymer chains together with carbon-to-carbon bonds. And that does a really big, that's a really big change. So that changes the material from a thermoplastic, which could melt when excessive heat is applied, to a thermoset, which would not melt when excessive heat is applied. So here you have kind of a description of a polymer chain before cross-linking. Apply heat, it'll melt kind of like a candle would. It's a little bit of an exaggeration, but kind of. And after irradiation, the polymer chain gets aligned. These carbon to carbons make these bonds, And once those bonds are created, that's the crosslink, and they can never, ever again let go. A visual that I was shown years ago that I kind of liked was, this wood block game that probably many of us have played. If you picture that as the insulation, or as the insulation molecule, the polymer chain, if you apply heat to this, it'll fall apart and melt, which clearly you don't want. What irradiation does is it randomly nails these blocks together, so when heat's applied, it doesn't melt. In wire and cable, there are two primary methods of cross-linking wire. One is generally referred to as chemical, and there's two processes of chemical cross-linking. One is called CV, which is continuous vulcanization, and the other one is moisture cure. That's chemical cross-linking. Champlain's method is irradiation, and we're going to talk about both of these processes. So chemical cross-linking relies on a chemically induced reaction caused by either heat and pressure at the point of extrusion or humidity in the case of moisture cure. So we'll first talk about chemical cross-linking. There are some fundamental drawbacks to chemical cross-linking, but to be fair, cross-linking, at the end of the day, it gets the job done. Whether it's done chemically or through an irradiation beam, the end product is cross-linked. It is a thermoset material. The drawbacks that a chemical process has is merely in kind of robustness of the product over time. And, that's kind of a big deal in the motor market, which is, I think, will become apparent as we go through some of these next slides. But from a performance or a manufacturing process, the insulation material in a chemical cross-linking process has residual peroxides in the material that over time, and particularly at elevated temperatures, are going to degrade the material from the inside out. You can also encounter post-cure cross-linking, which is where cross-linking will continue to occur after the process, and that needs to be, controlled. By contrast, irradiation, it's either being irradiated and cross-linked or it's not. As soon as that process is done, it's over. There is no more cross-linking that can possibly occur once it's out of the irradiation area. You can also have under cross-linking, where the cross-linking does not cure all the way through to the conductor. So you have product with a higher degree of cross-linking on the surface and then a lower degree underneath the surface, and that is not desirable either. And the process itself, you extrude the insulation on the wire at the extrusion crosshead, and in chemical cross-linking, it runs immediately into a steam and pressure tube, and you cannot really monitor or observe at the crosshead if you run into any post-setup issues at the extrusion process. So that's also something that can run awry if it's not paid close attention to. And the biggest thing between the two products is the high temperature robustness and life expectancy of the product. So CV, chemically cross-linked or moisture cure product, is a full-on 125 degrees C product. No issues there. In the right environment, it is a great product to use. When you get into the 150 degree range and elevated temperatures and varnish exposure, now you're going to start seeing some differences between the two, which we'll go through in a few slides from now. But this picture really kind of, everyone says a picture's worth 1,000 words. So this is a picture of an irradiated Champlain product on the right, the orange cable on the right, and then a chemically cross-linked polyolefin on the left. And it's after a 3,000 hour, 150 degrees C heat age. And depending on the standard that you're building to typically you're going to have a 3,000 hour heat age, or in the case of UL, for UL lead wire, it's actually a 3,600 hour heat age at rated temperature to attain that UL style. So after heat age, the Champlain product on the right remained pliable, had plenty of life left in it, was bent around the mandrel without any cracks. The chemically cross-linked product would have done a lot better at 125 C, but this product is sold and marketed as 150 degrees C. And after after the standard amount of time to attain the 150 C rating, after that 3,000 hour test, it really miserably failed the bend test because so much life was sucked out of it, it got brittle and cracked. Okay, so irradiation cross-linking, how does that differ? Irradiation is a method of cross-linking which utilizes, instead of chemicals, a high voltage beam of electrons to create the same carbon-to-carbon bonds which link the polymer chains together. It requires very specialized equipment, very precise controls, and the combination of the recipe for the Exar material and the irradiation technology together brings a product that is, you saw it in the first slide. This is our 50th year of having the Exar product as a motor lead in the market. And we've made changes to improve the flexibility, which we'll detail a little bit later. But that original Exar has remained unchanged in 50 years, and it's still being used in the market, which is a real nod to the engineers who designed it in the early 70s, because it is a very well-designed product. Here's what an irradiation unit looks like and what the Exar motor lead under the irradiation looks like. So you've got this room, and above it houses this super expensive, highly precise equipment. The radiation beam bombards the wire as it's going back and forth underneath the beam. And so we will control the number of electrons, the speed, the ampacity, the voltage, the number of passes underneath the beam, and all of that is controlled very precisely and measured at the end of the process at Champlain. So in addition to changing the material from a thermoplastic to a thermoset, which brings its own advantage, a lot of other performance attributes of the wire are improved that you really would like wire to have. So oil and fluid resistance is improved after cross-linking, resistance to heat on the high end, but also resistance to cold temperatures also. Abrasion performance is improved, crush compressive force resistance is improved, processing advantages, strippability and so forth, other attributes which might be specific to a customer. And in Exar's case, it's a blend of our processing and the recipe for Exar. The varnish release is just unmatched. It's industry leading for the Exar product, and we'll show some examples of that later. So the cross-linking process kind of takes the insulation material and sends it to the gym for 6 months in a really intensive workout regime and just bulks it up and makes it much better than the original. Okay, I'm going to switch gears a little bit and talk about Exar products. So we've spoken about the process between cross-linking, and I should mention, cross-linking is aligning those polymer chains together. Another common lead cable is silicone, and silicone is a thermoset, naturally a thermoset, so it does not melt when heat's applied, but it is not cross-linked, and we won't get into all that chemistry, but that is a common motor lead cable, and it is a thermoset, but it is not cross-linked, so we didn't really go into silicone before. All right, so Exar products. We have two 600-volt products on the market, and we have one 7.5 kV product on the market. And that covers, I don't know what percentage, 90% of all motor applications. You know, there are some higher voltages and maybe some a little smaller, but these two products pretty much cover the lion's share. So the Exar 150, what we now call 150A, because we have different variants of it. Some people also call it standard, kind of the standard product, the original product. That is still out there, 50 years and running. UL 3289, dual rated for 3271, which is a 125 degree C, but it's dual rated for inventory. You know, so you don't have to carry dual inventory, I guess. Some OEMs over the years do need to see that 3271 on the print, and so it stays there. 600 volt, 150 degree C, UL-VW1 flame rating. Here's where some of the differences come into play versus a chemically cross-linked product. UL recognizes irradiation cross-linked products as being more robust, being tougher, and the wall thickness that's required for the same voltage and the same thermal class is thinner in an irradiated product than a chemically cross-linked or a silicone product. And there's various reasons for that, but the differences might be small. Like on an 18 gauge, it might be the difference between a 30 mil wall and a 45 mil wall. So 15 mils on each side, 30 mils. You think, well, that's not that big of a difference. But when you bundle, you know, 6, 8, 10, 12 leads together, and you've got a motor housing that's a really tight, confined area, and the difference is a little bit bigger, obviously, the bigger the size. Now you're really talking an advantage when it comes to, you know, getting leads into a very tight space. So it's a smaller OD than EPDM or silicone. And the 150A has a UL rating for use in oil up to 60 degrees C. And we're going to talk about oil resistance in a separate slide, because that's a special consideration that we want to dig into a little bit. The other 600 volt product we have is called SFX or SFX-OR. SFX stands for super flexible, and OR stands for oil resistant. The original 150A, as great of a design as it is, its one Achilles heel is flexibility. When you get into larger sizes, and the user has to define that, let's just call it 2 gauge, 1 gauge, 1/0, somewhere around that area, a rubber type product, EPDM or silicone rubber, really starts to show that it is a more flexible product. So many years ago, we came out with the SFX and then got the oil resistant on the SFX. So it's now SFX-OR. And the beauty about this product is it's the same UL style, exactly the same, 3289, 3271, same CSA, 600 volt, 150 degrees C. UL dictates the wall thickness, so it's the same size as the original 150 standard. The big difference is it is more flexible than 150 standard. There's really not a great way of measuring that. I guess pounds of force on a certain size, you could do that. Really, you kind of got to feel the two side by side, but it's more flexible. You take a 4/0 of standard and a 4/0 of SFX. The SFX is noticeably more flexible, and it would rival that of EPDM and silicone, and it does it in a smaller profile, in a smaller OD. So those are the two 600 volt offerings. 7.5 kV would be the next voltage that we offer. That is only available in the SFX-OR. That's a UL 3575, 150 degrees C. This is our most flexible motor lead because the conductor that we use is a higher strand. It's a Class K 30 gauge strand. So in a 4/0, I forget, there's 2,000 some odd strands. In a 4/0 7.5 kV, there's 259 strands in a 4/0 600 volt. and that's just how the design is and the way that it's been brought to market. So that is our most flexible option. And just as a quick mention, we don't see this so much in the US, but we're starting to see a little more traction in different markets. We can offer these products 600 volt in halogen-free options, 3289, 3271, 600 volt halogen-free. If you ever have a request for that or a question for that, we do have that product that we can offer. Features and benefits of they're really kind of both the same for the 150 because they're such similar products, but the difference really being flexibility. They're radiation cross-linked, number one. So the Exar recipe, the Exar brand, and the radiation cross-link coupled together brings a lead wire to market that is very, very robust and has been for many years. It's a thinner diameter than the rubber-based products, easier to route for the winders in the process, and the SFX at least is very flexible even in the large sizes. Varnish release is second to none. I'd call it best in class based on what I've seen at OEMs and shops over the years, and what we've seen in our own internal testing, which we're going to show some images of in a few minutes. It's a very tough insulation. Rubber type products, silicone and EPDM and chemically cross-linked products are not as mechanically robust as an irradiated product. And when it comes to the SFX, it's highly flexible, easier to work with and install. It's 150 degrees C from a UL standpoint. So the benefit of that is it's suitable across, a lot of UL system classes. Class B, Class F, Class H can use a 150 degrees C cable. We're going to talk about that under special considerations. I do understand that some customers, when they order a Class H, will say, I want the lead wire to be Class H rated, meaning you're going to have to use 200 degrees C because Class H is 180. UL, as far as UL is concerned, you can use a 150C lead cable because it's a minor component, but if a customer says it's got to be Class H, then you've got to bump up to like a braided silicone. But you wouldn't have to as far as UL is concerned. From a CSA standpoint, our product is 150 degrees C. If you look at the small print on EPDM or CV products, they're very likely rated 125 degrees C by CSA for the reasons that we spoke to on the earlier slides. Very robust performance, the Exar product. So it's kind of an all-in-one product. You can use Exar in place of EPDM, in place of silicone on Class B, Class F, Class H. It's kind of an all-in-one motor lead for you. RoHS 3 compliant, and it's oil resistant and can be used in oil exposed applications. And again, we're going to talk about this in an upcoming slide, but oil exposure is defined differently by every customer and every application. Oil exposure, oil splash is different than submersion. So you really have to understand what the oil, what type of oil it is and what the exposure is and what the temperature is to understand the lead wire that you need to select. Just a quick summary. SFX is really can be your all-in-one cable. Very, very good varnish release, very flexible, robust temperature performance. And that's really key in a motor environment because we showed that picture earlier with the red cable that cracked after heat age and the orange cable that remained intact. That's a heat age. In the motor industry and some transformer industries, you build the units, in this case a motor stator, and then you bake it in an oven, to cure the varnish for 6, 8, 12 hours at an elevated temperature. Well, that's kind of a mini heat age. It doesn't get super hot. It's not at 150 degrees Celsius that I'm aware of, but that is a heat age. That process is slowly sucking life out of the wire insulation that's inside that oven. And it just sucks the life slower out of an irradiated product than it does a chemically cross-linked product by the nature of the materials themselves. So let's do some comparisons of Exar product versus silicone. We have slides on EPDM, and we have slides on kind of a non-EPDM chemically cross-linked product, even though they're both chemically cross-linked. So Class H 155, Exar, yes, it can be used in Class H. A 150C silicone, yes, it is a robust, thermally robust insulation. Yes, that can be used in Class H. And EPDM, not without special approval. It's more astute to a 125 degree C long-term. From the literature I've seen, you would need special UL approval to use EPDM in a Class H. And I'm seeing, I misspoke earlier, there are 150 degree C silicones. I mentioned earlier that Class H, you'd have to bump up to 200 degrees C. You would if a customer requires Class H. I'm not aware of a 180 degree C rated silicone, UL CSA anyway, but there are 150 degree C silicone products. I typically relate them to being 200 C, but that's not always the case. Varnish release. Champlain's product is excellent. Very, very good varnish release. Silicone is okay. EPDM is okay. We did some internal tests. I think from what we've all seen on the market, if you've been out in the industry long enough, and I've been doing this for 30 years, we've seen areas where both silicone and EPDM have cracked during the varnish bake process. From a size standpoint, XR is thinner, silicone and EPDM are larger. Oil resistance, up to 60 degrees C, UL recognition, that's pretty good. Silicone and EPDM, depends on the silicone. There are oil resistant silicones. You'd have to seek one out specifically, but they do exist. EPDM is, it's fair from what the literature says. You'd really want to be a little more careful with an EPDM product. It tends to absorb the oil at a lower temperature and a little faster rate, leading to swell. So that's what happens. It absorbs it and swells. Abrasion performance, XR products are very, very good abrasion. Silicone and EPDM rubber type products are not as good. Just that's what the insulation is. It's a rubber product and isn't as robust from those sorts of mechanical ways. So let's do some testing. Okay, so Champlain bought on the open market a chemically cross-linked UL 3289, 3271 motor lead wire, and kind of did some testing on it. It was new to the market at the time. This is several years old, but it was new to the market, and we were kind of like to see what it does. Our product is CSA CL 1503 1251. CL stands for coil lead. This product that was not printed, we don't know what the CSA was. Our product is irradiation. The CV product is obviously continuous vulcanization. Our product is UL, XR product is UL up to 60C. We performed some oil testing on the product. All three of our samples passed the oil test. All three of the samples of the competitive product failed. And failure means it swelled beyond what the standard allowed, which is typically 15%. And it failed a voltage test after that, kind of a voltage robustness test. We put it through a UL heat age. Our product passed, obviously. The competitive product, surprisingly enough, on a UL heat age did not pass, yet it was sold and marketed as a UL 3289. Scrape abrasion, 3, almost 4x better scrape abrasion, rubbing on the wire. Varnish release, our product passed. The competitive CV product did not. And our product is manufactured in the United States, which I think you would see on when we showed all of the facilities earlier. Here's some pictures. So we've got the XR product on the left. It's dipped in varnish 3 times. It's put in an oven, and it's an epoxy varnish, by the way. And it's put in an oven for a bake cycle. Then it's wrapped around a mandrel. It cannot have any visual cracks, which it didn't. The CV product, we needed to get a close-up because you couldn't, just to show the crack. That's a crack in the insulation, and you can see the insulation material is sticking to the outside, which isn't necessarily horrible. You wouldn't want it sticking all the way down the wire. I think that aesthetically is not what customers like to see. But the CV, every sample we tested cracked. So let's compare Exar SFX versus silicone, another very common motor lead. This was done on an 8 gauge. Silicone, as we've discussed, requires a little thicker wall. So the diameter of these two is about 30 mils difference, about a 15 mil difference in wall thickness. And again, you say, 15 mils, that's not huge. It's not huge, it's 15 mils. But when you're coupling a bunch of sizes together, or a bunch of leads together, you're now reducing the size of that bundle considerably, and the space in a motor housing is usually very limited. I was at an OEM a number of years ago who, when their stator is all done and the motor leads are all tied up and ready for the motor housing to go on top, they didn't have but a few mils of space for that housing to go over. They could not have used a rubber or silicone insulation. It would have ripped in fact, it did when they tried, it would have ripped the insulation off of the wire. They had to have something smaller and tougher. Sandpaper abrasion, here's where some of the mechanicals start to show through. So the 150 and the SFXOR have really very good sandpaper abrasion, very good scrape abrasion, and very good pinch or crush resistance compared to a thicker wall silicone product by sometimes 1.5, almost 2x. And what test stopped means is R&D stopped the test because it had so far outperformed, and we didn't give them instructions to test the failure. The test was stopped. I guess they needed the equipment or something. So we don't know where the failure mode was, but agreeably, this is substantially better than a rubber product. And on the varnish bake test, both samples that we tested cracked, and neither XR samples cracked. There's a picture of the silicone with the varnish. Again, varnish sticking to it isn't a huge deal, but a crack is. A crack is something that you can't have after varnish bake. Totally different test battery for a different reason, but same product set. XR 3289 varnish bake test wrapped around a mandrel, no cracks. The varnish here, they just didn't flake it off, but you can see that varnish is ready to peel off like a sunburn. EPDM UL 3340, that shiny part is the varnish sticking, and these kind of light gray fissures are cracks. Same with silicone, UL 3604 unbraided silicone, crack after varnish bake. And again, this is our laboratory testing on what we test every lot of our product to. EPDM and silicone don't crack every day in everyone's process. They're legitimate motor lead wires that are out there. I want this to be fair and objective. But are they more prone to a cracking at varnish bake? Yes, they are. And if you've been in the industry a while, have you seen that at either your house, at your shop, or have you seen it at, if you're with EIS, have you seen it at one of your customers? No doubt you have. Heat age. So here's different insulation materials, but it's just showing a difference between a chemically cross-linked continuous vulcanization XLPE after a heat age, how that can really affect the wire. And this is relevant because this product was on the market as a 150 degree C wire. And it came from an overseas supplier. It was very low cost. And so the customer is saying, hey, I got a 150C product here that is pretty cheap. we're like, yeah, look at it after varnish bake. You're getting what you pay for. And the product on the right is a Champlain irradiated product, maintains its color, really tight bend after the same heat age, remains pliable, and does not crack. Okay, that is now we're through the product side and the comparison side on the motor leads. Now we're going to get into a few slides on fluid, on special considerations. The first one we're going to talk about is fluid resistance. There's 4 or 5 slides, and I think we're about ready to wrap up. So fluid resistance in this market, it's typically oil resistance, insulating oils and whatnot. Needs to be a special consideration. The hotter the oil, the more attention you need to pay to it. Higher temperatures reduce performance. Really, you start to see the kickover about 60 degrees C. That's why UL has the test defined at 60 degrees C, at least for the motor lead UL approval that we have. But temperature really matters when it comes to fluid resistance, particularly oil resistance, but it can be other fluids. And a product that does not swell or looks fine after you put it in a beaker of oil at room temperature and leave it in your shop for a week. Room temperature does not mean resistance at elevated temperatures. So you really got to be careful with that. And the UL rating, there's hundreds of different type of oils out there. And the UL rating uses one. It uses a motor oil. And that's great. I mean, that's fantastic. It's their definition for oil resistance, but any customer would want to do their own testing on the oil, particularly if it's being submerged, and particularly if it's at an elevated temperature, even if it's not submerged. Really needs to do some due diligence on that side. And then separate from oil, other fluids. Solvents you see around a shop all the time, toluene and xylene and others. Okay, if you get something on the wire, you want to clean it up before you ship it out with a solvent. Not a big deal. You wipe it on, you get the grime off, it evaporates in literally minutes. Not a big issue. You wouldn't want to soak it to clean it in toluene and then say that lead wire is good to ship out a week later. That would not be appropriate. They're just too harsh of chemicals to use. High temperature deformation. So in a varnish bake process, goes into the oven, sits there for hours and hours, and you take it out. If the cables are big and heavy, if they're wrapped and lined in a way where tie cords maybe cut into them a little bit, a few mils. Maybe they're draped over a metal edge that leaves a mark after heat age. That's possible. That can certainly happen. It's caused by excessive stress at elevated temperatures, like a varnish bake. But it's not the end of the world. I mean, that's a little deformation. Aesthetically, it's not great. Customers won't want to see that in the visual parts of the lead that they can see. But UL accounts for that. They account for deformation. UL sets the wall thickness that they require for each insulation type and each UL type. So let's just go with an 18 gauge again. It's 30 mils. That's there for a reason. And deformation is one of them in robustness and abrasion and other things. But UL allows up to 50% deformation. That sounds like a lot. It is a lot, but it is accounted for. It is tested for, and our products, just so you know, in that test will average around 10%, maybe 11%. It's not a huge amount. It's accounted for in UL. So if you see it in your shop, okay, if it's really deep, all right, you might want to look at the process. But if it's just surface, it's not the end of the world. And so how do you fix it? Well, what we've seen is customers using alternative wire management in the oven setting. Maybe they put a reusable sleeving on it. maybe the tie cord, instead of being like a piece of dental floss, maybe it's a tape. It's a little bit wider, so that pressure is spread out among a tape instead of on just a round tie cord. There's various ways that you can address it. Just know that if you see it, it's been accounted for in the design and in the UL style. We talked about this UL 1446 Class F and Class H motors. UL sets the requirements for what the thermal class of the raw materials need to be in the class. A major component, one that's in the guts of the stator or the guts of the system, must be the same class as the rating. So a Class H rating has to use Class H varnish, for example, and slot liners and stuff that's all inside. Got to be Class H. The motor lead, because it is brazed on the internal, but then it goes external. That is a minor component that is allowed to be one temperature class lower. So a Class F could use a Class B temperature, could use a 125C. Class H, a 180 rating, could use 150. The motor lead market at this point in time is really at a minimum 150 degrees C. You don't hardly see flat out 125C UL products. You do, they're out there, not to say they don't exist or aren't out there, but they're in the market that we play in, it's pretty much, you're looking at 150 degrees C rated Exar, silicone, EPDM, or maybe another CV type product that's not EPDM. That's it. We're on the summary page. So Champlain XR motor lead cables offer industry-leading performance across a wide array of performance attributes. It has been a trusted and used brand for 50 years. This is our 50th year. We came out with the XR in 1972, and that original XR has remained unchanged, which I'm sure you can find a product that has been unchanged after 50 years, but it'd be a pretty short list. That's how good that original design was. When you look at the SFX version, best in class flexibility, OD, varnish release. I mean, it's just an all around great lead wire, full on 150 degrees C UL and CSA, can be used in Class H systems, and every single foot we make is produced in the United States. And that is it. I hope there's some questions. I'm ready to answer them.
Perfect, Dave. Thank you so much. This is great information. I do want to remind everybody that you can send questions through the chat. Let us know if there's anything that you'd like additional information on, or something that you think could use some additional follow-up. We appreciate it. I do have a few to start out with. It's one that I think we might have answered as we continue to go, but is the irradiation cross-linking technology available for any cables that are rated to a 200 degrees C?
200 degrees C. Short answer, yes. Long answer, I'm not aware of an irradiated product that is UL and CSA 200 degrees C.
Okay.
And at the risk of going into, way too much detail than you're probably interested in, Champlain has irradiated 200 degrees C, 225 degrees C lead cables for other markets, for the automotive and commercial vehicle, and really any other market. We don't have a UL style on those because of the way UL tests product and some of their requirements, regardless of the style. The 200 degree product we have, as robust as it is, and it's very robust with UV and temperature. I mean, 225 degrees Celsius is hot for 3,000 hours. I mean, that is a robust product. It's very fluid resistant. It is a really, really highly engineered insulation, but it's just not a good match for a UL test. And I don't have a lot of the specific details, nor should we really go into that much on this. Yes, it does exist. And we've sold it actually as a motor lead in an area that did not require UL. I think it was a motor lead that went on a locomotive. But so yes, it does exist, but not with UL and CSA.
Perfect, thank you. An additional question, can XR SFXOR be an alternative for Hypalon or the XLDUR?
Absolutely. So we've marketed the SFX versus Hypalon for a number of years, and Hypalon's older than XR. I don't know precisely when that was invented. It might have been the 50s, like when extrusion was invented or something like that. Yes, it can be used it can be used to replace Hypalon. Somewhere I have a document on a comparison between XR, Hypalon, and neoprene. And if you can put your contact information either in the chat or get it to Lindsay or get it to your EIS salesperson, or find me on the Champlain contact page and get it to us, I can get that to EIS and to you. Short answer is yes, it can be. XLDUR, I don't see that out there very often, but the fact that you're asking about it means that it is out there. And I'd have to look, I think that's a Belden trade name. I'd have to look at the spec sheet on that. Short answer, it's a motor lead wire. Yes, I'm 99% sure you can offer SFX, but I guess out of due diligence, I'd like to take a look at the XLDUR spec, and I'll make note to do that. I just hope we can get in touch with each other.
Yeah, absolutely. There's one question that I'm really excited. I think I can answer. I always like that. The question is, where can we get this cable in mid quantities and short lead times in California? And the good answer is that EIS does stock this cable. So we are more than happy to help anyone who's looking for, cut to length or certain quantities or lengths. And we do have the ability to cut to a certain length for anyone. So if you have an EIS representative, you can absolutely follow up with them or any of our branches in California. You can also send a question right here to marketing. So the contact information that you have for the webinar, we will make sure if you follow up with us, we can get it to the right place. So thank you very much. EIS is more than happy to help you get that in this short lead time, quick turnaround. One more question for Dave. Does the comment regarding varnish release also apply to epoxies?
Good question.
Did we stump Dave?
The answer is maybe. So frequently, not in this market, not in the motor market, but frequently customers will want to take our irradiated product and put it in a epoxy where they want the epoxy to stick. And irradiated products, by definition, really don't like things sticking to them. You really have to engineer it in a way that would allow things to stick to them. And so the short answer is you probably are going to have a tough time getting it to stick, but we could provide a product that would give it a good shot at sticking if that's what you wanted it to do. And if you don't want it to stick, then I think I'd have to suggest getting with us one-on-one on a kind of technical conversation, determine the type of epoxy you're using, and just kind of make sure that it's going to stick or not stick, whatever it is you're looking for it to do.
Perfect. One more. Is this technology available with both bare and tinned copper conductors?
Excellent question. By and large, or in fact, 100%, the motor lead that we make is tin copper because generally it is brazed, or I don't think really solder is the right word, but maybe it is. Certainly it's The tin is there for a very specific reason. Does UL care? No, they don't care. So yes, we could make this product in bare copper. That'd be a special make, but there's no reason why you couldn't use bare copper.
Thank you. And then, so with the obvious advantages that you've gone through on the irradiated cross-linking, why do some manufacturers choose to do the continuous vulcanization?
Oh, excellent question. So continuous vulcanization is remember, it's not as robust performance. It also comes to market at a lower price. So depending on what market a manufacturer is looking to go into, CV might fit their needs perfectly. CV is used all over the place every day, millions of feet. I mean, it is a legitimate 125C lead wire that's used in automobiles and motors and all the pieces of electronic equipment all over the place. So if that's a manufacturer's market, CV would be a natural. Irradiation, Champlain's focus across all of our product sets, including motor lead, is kind of the higher performance tier. That's just where we kind of have our sweet spot, and that was defined at the inception of our company. So if you remember, we started out in thin wall airframe wire, and hooking up airframe, passenger jets and fighter jets. That's pretty high performing stuff. When we decided to get into irradiation, it was because that was the level of technology we needed for that market. There were irradiated products we used in that market as well, and in this motor lead market. And the equipment, by the way, is crazy expensive. So you don't just decide to go into irradiation and spend that kind of capital outlay for even just one beam. They're like $4 or $5 million all in for a beam, or an electron beam. You're targeting that market for that particular reason. So that, I hope that answered your question. It's I see it as kind of the market that you're going after, but CapEx might also be a reason.
No, I think that was perfect. If no one else has any other questions, I think that answers everything that we got in through the chat and from people who are in attendance. I just want to say thank you so much to everybody who logged in today and who listened in. We really appreciate it. And thank you very much, Mr. Dexter. This was really great information. I think it's really important for all of us to know and understand the benefits when we're talking about the different products that are out there. So we really appreciate your help and your information.
Well, thank you, Lindsay. Thank you, EIS, for the time. I appreciate it.
Absolutely. So for all attendees, we will send a follow-up so that you have both a recording of this in case you have any questions and want to go back and check. We're also going to send out the information that we shared today so that you have all the information you need. Thank you guys very much. Everyone take care.
Thanks. Bye, everybody.